Okay.
Let's wait for a second.
Waiting.
There we go.
Okay. Hello. Is this working? Hello. I am Jamon, and I am a student from the Victoria University of Wellington, and I will be presenting proving false and object-oriented verifiers by exploiting non-termination, which is my accepted paper for this workshop in particular. The purpose of this paper is to present 3 examples where we break object-oriented verifiers with programs that we've written. I say break, meaning that we give a program that the verifier will prove as correct, but the program will ignore the contract that we have written for it. The verifiers we looked at for this were these 3. They are all for object-oriented languages, and they're all broken using pretty much the same general idea. I ordered them from the least complex way of breaking it to the most involved. Now, the way that we broke these languages was using the idea of non-termination. So we would always start off with a method or function that asserts that some contradiction would hold. And in every example of this, we would write asserts false on that method. And we then want, in some point in the code, to call this. And to do this, we would actually delay the execution in some way so that the function or method would actually never exit. This part of the exploits that we used, where it varies between all of the examples and is really the source of why things are broken. The final step that we use to actually make the programs terminate is that we can use ghost code to hide these proofs that are not terminating. Ghost code is used in a number of verification languages where you can write proofs of your code's contracts, but the proofs are not used during runtime. So these lines of code will be omitted when the program is compiled, for example. It's worth to mention that before going into the examples is that there are 2 types of correctness that you can have for programs. We have partial correctness and total correctness. The difference between the 2 correctness is how termination is handled. In a partial correctness, termination is assumed. So a program that is verified to be correct in terms of partial correctness will either terminate and follow the contracts that you've written for the code, or it will not terminate. And it doesn't really matter what it does at that point because it doesn't terminate. Total correctness will prove termination on top of that. So it does everything that partial correctness does, but then it will in addition prove that termination occurs. And this is usually done with the addition of what you would call a decreases clause, which proves that eventually there's some property that decreases over time, meaning that eventually the code must end at some point. The first example is in Gobra, which is a verifier based on the Viper infrastructure, which is used for verifying programs written in Go. We start off this example with a function recurse, which takes no parameters and returns 1 int. And all that we do inside of the body of this method is just call recurse. So the method calls itself. Now, when verifying this, to prove the contract, we will look at the one statement that is in here, which is recurse. And if the code will see that this recurse method states that ensures false in its contract. And so we can use that to then improve the false condition that false will hold on exiting this function. Now, obviously that we can see that this recurse method uses its own post condition to prove.
Sorry, can I just interrupt you there?
Yes.
You actually have to prove non-termination in order to be able to infer false from that? Have you got a proof rule
well,
for that?
actually, with the Gobra verifier, it only does partial verification. I actually forgot to mention that. So it does partial verification, so it doesn't check for termination at all.
Yeah, but how do you infer, using the rules that you showed before, how do you infer false from that? You have to know that it doesn't terminate.
Well, it doesn't terminate. The only way that this terminates is through.
Yeah, you know it
stack
doesn't terminate. I can see it doesn't terminate. But I don't see how the rules, I don't see how the proof system.
Like the idea is that this is not his work, this is Gobra. So we don't know. We are just experimenting with this tool and we are seeing what happens.
But in this case, it's a type system level proof, right? It's like inferring the type button, which the type system can do, so the proof is pretty straightforward. It's immediate, right? Because you look at what this function returns, and it returns the same as the recursive code, so immediately we have like this non-terminating, right?
Well, again, that to me sounds like an intuitive proof, not a proof using the proof rules. What I'm asking is, how does the proof system tell you that? But look, I don't want to derail your talk with a basically side issue.
Just to add one small thing here, it's really like an invariant, right? It's just that you assume that the postcondition of recurse holds, and then you do the proof. It's like a proof by induction, but the base case is missing.
Right, okay.
But this is just the verifier assumes that the postcondition of recurse holds, so it assumes that false holds, and then it calls it so it can prove that it holds. It's just that this proof is wrong in a sense because it does not terminate, but this is the proof rule that is used.
All right.
So what does this syntax mean, the underscore int?
Underscore int, that is, well, underscore is just the name of the variable returned. This will be used, like, if later on in the code I actually write r int, and then I can say ensures r equals 0 as the postcondition. So you can just give a name to the return type. That's what that is. Underscore just means that there's no name.
Just an anonymous variable.
Yeah. So this function, it proves itself in a pretty absurd way. But this is technically fine when you're only considering partial correctness, because false is a contradiction, but because this would never terminate except for in a Stack Overflow exception, there isn't really much of an issue here because we're only looking at partial verification. However, in the next function is when we break this. So the function test has no parameters and doesn't return anything. And there's only one statement, which is a ghost variable assignment, which is unnamed, and it calls recurse, which is basically the value of the int that recurse is supposed to return. Now, obviously this is completely recursive, doesn't terminate, but this also ensures false, which holds on the exit of this body of this method. So the postcondition false on this function will also prove to be true in this case. Now, this is unsound when you're considering partial verification, because this function test will actually now terminate. And in this example, I just give a quick example of why this is bad. So you see here that this statement, the ghost variable assignment, will not be present at runtime. So the function test is essentially just an empty function that does nothing. And so we define a new function called bad with no parameters and an int r, which all it does is it calls test and then returns 1. But we give the post condition that r is 0, that it returns 0, which is wrong. It violates its contract by returning 1 instead of 0. But because we have put test in here, it ensures false. And because r equals 0 is a weaker post condition than ensures false, it proves this. And we have made a program that terminates, but disobeys its contract in Gobra. So for this reason, this is why I believe that ghost code in partial verification is not sound, unless maybe it's restricted or something. The second example is the key verifier, which was made for verifying programs written in Java. Key only really supports very old versions of Java, like before Java 8. It doesn't support generics or lambdas or anything, but it's still we can still exploit this in this example. So one thing that key does is that it will verify contracts separately from each other. So in order to verify a full program with contracts on each method, you would select one of the contracts, and then key would run a proof on that one contract. Now, in this example, it looks very similar to the previous one, except that there are two recurse methods instead of just one. And both of them return one int and have no parameters, and they both ensure false. They both call each other, so recurse 1 calls recurse 2, and recurse 2 calls recurse 1. This has the same behavior as the previous example, except the execution loop is between the two functions, or two methods, instead of just staying inside one. Now, when key is proving one of the contracts, as soon as it encounters a method with a contract, it doesn't look any further. So this is why when looking at recurse 2, we can say that it ensures false, and it will verify false on recurse 1, and vice versa. Recurse 1 will ensure false on recurse 2. And this is because key is not aware on each verification of the contract. It's not aware of the body of the other method. So it doesn't check to see whether it's actually recursive. It just verifies the post condition according to the post condition of the called method. Now, the result of this is we can do the exact same thing. We can make our test method, and we just initialize one int, which is the result of recurse 1 that ensures false, and we return. And because it's a ghost method, a ghost code, it's not present at runtime. And then you can do the same thing with this test method. You can just put it inside of another method, and it will immediately prove any post condition that you write. Here you can see this is what happens if you do not write false, ensures false on both methods. You can see that if ensures false is only on one, and it sees that recurse 2 does not have a contract written for it, it will then look to the body of recurse 2 to try and synthesize a post condition for recurse 2 to prove itself. And at that point, it will see recurse 1, which is obviously recursion. Key will not accept this, and it will not prove this. The final example is Dafny, which is a bit more complicated. Dafny is much better at detecting termination, but it still makes assumptions that are not sound about termination. So in this example, we will define a trait called uninhabited, and it has one abstract function method called get that returns an int and ensures false. And this is the same method that we use that ensures false in the previous examples, but we don't actually write an implementation for this. We just leave it abstract. We then make a class omega, which has one constant called omega, which is a function from the omega instance to an instance of uninhabited. Now, this function promises to return an instance of uninhabited. You might notice that we don't write an implementation for uninhabited here. So this function here basically assumes that, or ensures that when it's done execution, that it will return you an instance of uninhabited. So in the constructor, we initialize this field with a lambda, which takes an omega object and calls o.omega of o. And this is a lambda calculus term, known as the omega combinator. which has recursive properties. It is possible for this to not terminate. But Dafny does not recognize this and will allow us to use this as a field in our code. So once we've done this, we can bring it all together in the final method called test, which ensures false. And we first initialize a variable O, which is a new instance of omega. And we do our familiar ghost variable declaration. And so we call O.omega of O. And so this line of code here, O.omega of O is recursive. It doesn't reduce. It will basically just keep calling O.omega of O forever until a stack overflow. And then after that, we call get. And get is the method that we wrote up here, which ensures false. So that means that this ghost variable declaration ensures false and will prove the post condition false on this method as well. And we end up with the same result in Dafny. Now, the reason for this in Dafny was actually this happens in Dafny is because of an assumption that the developers have seemed to make. So I have a quote from the reference manual regarding lambdas, and it says, "Lambda specifications do not have decreases clauses because they do not have names and thus cannot be recursive." Now, this is obviously false because we used a lambda to create recursion in our code. And they miss the fact that lambdas are able to read parts of memory that contain themselves. And so this is true for fields of a class. Lambdas are able to read fields of a class that are lambdas, and lambdas can also read indexes of an array that are lambdas. And so it's possible for a lambda to call itself by calling that part of memory and then putting itself in that part of memory and then causing a recursion. So there's a lot of ways to cause recursion in Dafny by using lambdas, because there is actually no way to even prove termination with lambdas because they didn't give you that feature. Writing a decreases clause for a lambda will just result in a syntax error. So with this in mind, if the developers of Dafny did not recognize this, then in OO, it may be true that termination is very difficult to check for, especially with features like lambdas, generics, and dynamic dispatch, probably others, where in OO, there's a lot of features that we use and are the basis of a lot of patterns that we use for programming. But these methods can be abused in probably a lot of ways to create recursion that's not easy to track. Like you could imagine a generic class of T, which basically is a collection of T, which has methods like add and get, but also has like a map of T, map T to A, which maps all of the elements to another element by using another lambda. And at this point, you could make T inside of a generic function, a lambda, and then at that point, you have a mess, basically. You can probably find many different ways to create termination with that. And the way that Dafny checks termination is really just looking at a bunch of methods and seeing what methods call other methods. And if it sees a circular loop of methods calling each other, then it would ask you to supply a decreases clause. But with all of this complicated lambda business, how would Dafny, prompt you to provide decreases clauses for something like that in an OO language? So I think that's just something to think about. That is all of the examples I had for today. Thank you.
So thank you, Jamon. So is there any question from the audience?
Yes, any questions?
So I find it very surprising that the designers of Dafny thought that termination could be. Oh, sorry. I find it very surprising that the authors of Dafny thought that termination could be ensure with such a simple criterion by just looking at the methods and see if they follow a cycle and omitting the fact that at runtime cycles may be created that are not known statically.
Well,
but
yes.
That's just like a basic thing.
That's kind of what my point was with the last slide, is that during runtime you can create using, lambda.
Yeah, I know. So how come they didn't know that? I mean,
I don't know.
Did they know?
Those guys are not stupid.
They're not. They've done a very good job with Dafny. It's very
maybe
surprising to
knew
me
and
that
they thought it was okay like this. A bit like the TypeScript developers who say, yeah, some parts are unsound, but it's fine. Or is it like this?
Well,
how did they argue that their tool was really sound?
On their GitHub page, there's a wiki article. I didn't reference it here, but they say that Dafny is designed to be sound except for bugs, obviously. And it's basically, they say sound but incomplete, which is it's sound, but some things cannot be proved with Dafny. And that's what they claim to be the design of their program. So this is
okay. So,
a very
so they just didn't have this particular source of unsoundness in mind.
I suppose they just didn't. They didn't.
I imagine that they are distracted by other pressing concerns. I have to say, that's the only way I can wrap my head around it. How can people that are clearly not stupid miss something like this?
Mm-hmm.
I would like for them to tell me.
Have you contacted them?
There's been various GitHub issue reports on this here. They haven't fixed it yet. It's been around for a few months now, I think, the issues.
Yeah.
We haven't seen any solutions. I've seen people making discussions on how they might fix it, but I haven't seen much else.
So how about the other two tools? I wasn't aware of them. Are they like well-known tools in the community?
They well known. Both of these tools were introduced to me. They seem like tools that were not super unfinished. Key is pretty old of a tool, which claimed full functional verification. Gobra is basically one of the tools based on Viper. It was the most complete. There's other tools based on Viper, like Prusty, which is super incomplete. But Gobra was I think the best one that is based on Viper.
Key was definitely regarded as a pretty well-developed system at the time that it came out.
If I can add about Gobra, because I'm from the group. I'm not a Gobra developer, but I'm from the group. It's a tool that we have built on top of Viper for a few years now. It's right now used in a really large-scale project to verify the new internet architecture. And the idea is that at the time of it goes hand in hand, right? It's still a prototype that we try to use to verify something large, and then at the same time we are aware of many bugs in it, but we try to improve the tool. I mean, I don't personally, but we try to improve the tool at the same time as we advance. And these things with termination, I know of many other unsoundnesses in the tool, but that can be easily fixed. And so here, I don't think
this one is not so easy to fix, right?
this one is easy to fix. You impose that in Ghost code has to be terminating, right?
Yeah, but you need to make a termination system to do it.
Yeah, but then you might go back into the realm of incompleteness. You have some code that should be terminating, but it's hard to prove to terminate. But I'm not sure, but I think in Gobra you have decreases clause also, right? It's just that termination is optional. Like in Viper, you can prove that your code is terminating. And this, you could just here force Ghost code to be terminating. Then if we add lambdas like in Dafny, maybe there are other problems. And I'm looking for maybe the next talk to see fundamental problems.
Okay. I think we are on a good time for this one. We can have more question and a group discussion after the second talk.
Thank you.